So in section 3.2, we are talking about empirical formulas, molecular formulas, and the percent composition by mass that formulas have. So whenever you're finding a percent of something, you have the denominator being your entire sample or the entire thing that you have, and then the thing you want to focus on is in the numerator. If we wanted to know what percent of points you got on an exam, we would take the total points of the exam and the points that you got. If we want to know the percent of people in the class who have lab on Monday, we would take the total people in the class and then focus on the people who have lab on Monday. So that's what we're doing here in this problem. We have a sample of compound and we've analyzed it by mass to figure out how many grams of each element that compound contains. So what we need in the denominator is the total mass of the compound. And if I add up all these masses, 34.82 grams of nitrogen, 88.11 grams of chlorine, 10.02 grams of hydrogen, the total mass that I get is 132.95 grams of the compound. And when we look at the nitrogen, there are 34.82 grams of nitrogen in that 132.95 grams total. As a percentage, once we get the fraction, we multiply it by 100 and then keep this unit percent to change 0.2619 into 26.19%. And that is the percent of nitrogen by mass that is found in this compound. All right, when we do this for chlorine, the 88.11 grams represents 66.27% of the total 132.95 grams, and the 10.02 grams represents 7.537%. I did that up here because I ran out of room. When we add up all these percentages, you can double check and make sure they come out to 100% or fairly close to 100%. In this case, we have 1% that goes 3 past the decimal, the others go 2 past the decimal, so we end up with 99.997%, or effectively 100% for that. We don't need to have an analysis with grams of calcium and grams of nitrogen to do this. If we have a formula, we can do the same thing. We would take the grams of the element that are in that formula, the grams of calcium in a mole of calcium nitrate, and divide it by grams of calcium nitrate that are in a mole of calcium nitrate. So we can do it with just a formula. Let's review calculating the formula mass of calcium nitrate. So the formula mass that we came up with, 164.10 AMU, comes from 40.08 AMUs of calcium, 28.02 AMU of nitrogen, and 96.00 AMU of oxygen. So we add those up to get the 164.10 AMU total. So this total 164.10 AMU will go in the denominator, and each of these will go in the numerator to get our percent by mass. So this is what that looks like. The amount of calcium over the total amount times 100% would give us 24.42% calcium by mass. Doing the same thing with nitrogen gives us 17.07% nitrogen by mass. And then lastly with oxygen, we get 58.50% oxygen by mass. Then when I add these up, it is definitely close to 100%. It's 99.99%. And that's just maybe due to the rounding of these three. Since we rounded them all 2 past the decimal, we're rounding this 2 past the decimal, so you could end up with 99.99. Sometimes you can end up with 100.01%. Those are okay. If you end up with only 86% or 152%, then you should double check your numbers. In addition to getting the percent composition from the formula, we can go in the reverse direction and we can get the empirical formula, or the simplest ratio of elements, from the percent composition by mass. I was looking at these steps and I noticed that the example I have does not need the last step. It says simplify ratio if needed, and this example doesn't need it. So I want to do a different example that does need it so that we can see how all the steps work. You can still try this example. The answer is in the answer key for chapter 3, so you can practice that, but let's practice a couple of other ones that need this last step. And so what do I mean by simplifying the ratio? So if you end up with a ratio of something that's 1.99 to 1, then that effectively can be rounded. That's a 2 to 1 ratio. However, if you end up with a ratio that's 1.51 to 1, that's a little bit far. We don't want to round that to 2 to 1. That's not a good idea. Instead, what we could do, since this is basically 1.5 to 1, we have this half in here, what we can do to make this a whole number is multiply them both by 2. So if we multiply both of these numbers by 2, the 1.51 becomes a 3.02, and then the 1 becomes a 2. So this is effectively a 3 to 2 ratio, which is different from a 2 to 1 ratio. So we don't want to just round this off to be a 2 to 1 ratio when it's not. It's a 3 to 2 ratio. So when you're doing these ratios, if you end up with something that's really close, you can round it. If you end up with something that's a half, 0.5 of something, so if you end up with a ratio where one of the numbers ends in 0.5, then multiply those numbers by 2 to turn that 0.5 into a whole number. If you end up with something that's something in a third or something in 2/3, you can make that a whole number by multiplying by 3. If you end up with something that's something and a quarter or something and 3/4, 0.25 is a quarter, 0.75 is 3/4, you can change that to a whole number by multiplying by 4. And when I say multiply, remember that we multiplied both numbers by 2. We didn't just multiply this number by 2 and end up with a 3 to 1 ratio. We ended up with a 3 to 2 ratio because all the numbers need to be multiplied. All right, so let's do this compound that is 52.92% aluminum and 47.08% oxygen by mass. So our first step is to assume that we have 100 grams of the compound. So if we had 100 grams of this compound and 52.92% is aluminum, then that would mean that we have 52.92 grams of aluminum. So that's an easy way to start working with grams. And the other 47.08 grams would be oxygen. Now the next step is to convert to moles. So we convert this to moles using the molar masses of these two elements, and we end up with 1.961 moles of aluminum to 2.943 moles of oxygen. So this is the molar ratio of the elements, but the problem is that we can't have a compound with this kind of formula. This is a little bit weird. We need these subscripts to be whole numbers, so we need to know the whole number ratio of these elements. The empirical formula is the simplest whole number ratio. So the next step is to divide the moles by the smallest number of moles. Because if we divide these numbers by 1.961, at least we know we'll get one whole number. So that makes this 1 mole of aluminum, so we got a whole number there. And then we have to do the same thing to every element in the substance. When we do the second one, we don't get a whole number for oxygen, we get 1.5. And we mentioned how this is a little bit too far to just be rounding up to 2. So we have this situation, we end in 0.5, so we can multiply both of these by 2. This stays a whole number, and this now becomes a whole number. So we can write a formula with this kind of ratio, and here we have Al2O3, aluminum oxide. Let's try one more example where we have to do all 4 of these steps. So here was that step 4, multiplying both by 2. Sometimes you do come out with all whole numbers at this step, and that's great. You're done after step 3, but let's try another example where we have to do step 4. Let's try another one with 86.40% tin and 13.60% nitrogen. So we are assuming we have 100 grams of the compound and 86.40% of that would be 86.40 grams, and then 13.60 grams nitrogen. So then we have to convert these to moles, and that gives us 0.7278 moles of tin for every 0.9707 moles of nitrogen. So let's go ahead and divide this by the smallest number. And that gives us 1 mole of tin for every 1.33 moles of nitrogen. So this is not really a 1-to-1 ratio. The 1.33 is not small enough to round it down to 1. It's like 1 to 1 1/3. So to get this 1 1/3 to be a whole number, we should multiply both of these by 3. And when we do that, we get 3 moles of tin for every 4 moles of nitrogen. So our empirical formula for this one would be SN3N4. So we've talked a little bit before about the difference between empirical formula and molecular formula. The empirical formula is the simplest ratio, which for covalent molecules is not always the formula of the molecule. So we had examples like this, C6H12O6. The empirical formula, the simplest ratio, is CH2O. And the molecular formula is a multiple of this. So this is really 6 times what the simplest ratio is. So what we need to know is figure out for molecular formulas, we want to know what this number is. So if the molecular formula is 6 times as big as the empirical formula, if we have the molecular mass and we divide it by the empirical mass, then for this particular example, the molecular mass of this compound is going to be 6 times as large as the mass of the empirical formula, because this is 6 times as much. So we can figure out if we don't know this number, so for examples where we don't know the number, we can figure it out by doing this division. So for this first example, we have the molecular mass, and we need to divide it by the empirical mass. To get the empirical mass, we just add up the empirical formula, a carbon, 2 hydrogens, and an oxygen, and we get 30.03 AMU. So we've done that step. The next step is to divide the molecular mass by the empirical mass. So here's our molecular mass. We're told it's 120.10 AMU. If we divide it by the empirical formula mass, which we just calculated as 30.03, we get that it is 4 times as big. So our molecule is 4 times as big as CH2O. So our molecule must be C4H8O4. And we can double check that by adding up what the molecular mass would be, and we should get something close to 120.10. For this next problem, we're going to combine getting the empirical formula from the percent and getting the molecular formula by using the empirical formula and the molecular mass that we're given. So if we want the molecular formula of something, we need to find out what multiple the molecular formula is of the empirical formula. We do that by dividing the molecular formula mass by the empirical formula mass, like we just did in problem 4 above. However, this time we have a problem in that we do not know the empirical formula. So we don't know the empirical formula mass, and we also don't know what to multiply n by once we find out n, because we don't have the empirical formula. So we really need that first. So how do we get that? Given the percents, remember our first step is to pretend we have 100 grams of this compound. So we pretend that we have 100 grams of the compound, and 40.66 grams would be carbon, 8.53 grams would be hydrogen, and so on. The next step is to convert all of these grams into moles with the molar masses. So that gives us these numbers of moles of carbon, hydrogen, nitrogen, and oxygen. And then we're going to pick the lowest smallest number of this, which is 1.693, and divide all of these by that. All right, so this gives us whole numbers this time. We don't have to do one of those steps where we simplify the ratio. When we do this division, we get whole numbers for each of the elements, and so we can make the empirical formula directly here. So we have come up with the empirical formula of C2H5NO, and when we calculate the mass of that, that comes out to 59.08 AMU. So now we're making a lot of progress. We can do this step up here. The molecular mass is 118.14 AMU, and our empirical mass we just calculated is 59.08 AMU, and so that comes out to be 2. So our molecule is twice as big as our empirical formula, and that would make our molecule C4H10N2O2. And so if you double check this, you should find that this has a molecular mass of 118.14. The empirical formula of this molecule is indeed C2H5NO. And if you wanted to figure out the percent by mass, you should come out with the same percents that the problem had.